Mhm. Good morning, everyone. So, the topic for today is the different types of semiconductors. And the learning objective of this session is under learning outcome or learning objective 1.7. And to read on your screen, it says here explain the principles and characteristics of the types of semiconductor materials. Okay, so let us proceed. So we have new and emerging semiconductors, right? And there are different voltage drops of different semiconductor materials depending on what uh, materials this particular semiconductor is made of. Okay, so although some of the materials here are already existing, but long time ago, that they are included in this table in order for us to compare its band gap energy and typical voltage drop and AP engine. By the way, what what is a voltage drop in a PN junction? Remember our discussion that a diode is or a semiconductor material is made by combining or joining P and N-type materials. So that's P-type and N-type materials. And when they are joined together, there would be an existing depletion region, and that depletion region would normally have its intrinsic quality of what we call voltage drop. Despite that is no voltage supply, then still it will inhibit a voltage difference between this junction or across this junction. Okay, and that will constitute to the band gap energy. Meaning, as we recall, band gap energy is the amount of energy that you need to overcome in order for the current to flow through this semiconductor. And remember also that semiconductor has properties of both conductor and insulator. That is why its conductivity can be altered depending on the factors surrounding it. And one of that is the applied energy. Okay. So let us continue. The first material here in comparison is germanium. Okay. The voltage drop in a PN junction is 0.3 volts. And the band gap energy, that's electron volt in terms of electron volt, and that is 0.66. For silicon, the typical voltage drop is zero point 0.7 volts, and the band gap energy is 1.12 electron volt. Gallium arsenide, band gap energy of 1.43 electron volt, and a typical voltage drop of 1.2 volts. Silicon carbide, we have 3.26 electron volt, and typical voltage drop of 2 to 3 volts. We also have gallium nitride with a band gap energy of 3.4 electron volt and typical voltage drop of 3 to 4 volts. Also, and lastly, we have indium phosphide 1.35 electron volt or a voltage drop 1.3. By the way, let us define the difference of electron volt to volts. Okay. So when you applied a volts or potential difference into an electron, it either loses or gains. Electron volt is the amount of energy lost or gained by an electron when it moves through a potential difference. Here are applications for this particular semiconductors. So germanium has the lowest voltage drop. And what is its implication then? It means that having that lowest voltage drop, meaning there's it has also, or it is a kind of semiconductor which will allow current to flow by the smallest amount of energy needed. Okay, so it is suitable for low power applications and high frequency devices. Okay. The only uh, disadvantage of germanium is it has higher leakage current at high temperatures. Let's take a look at silicon. So silicon is the most widely used semiconductor material with a zero point 0.7 volts voltage drop, balancing efficiency and stability. So it's not germanium, but rather it's silicon. We also have this compound semiconductor. If we recall, elemental semiconductor includes, for example, germanium and silicon. But the moment that it is composed of two elements, then it forms a compound semiconductor. One of that is the gallium arsenide. It has higher voltage drop as compared to elemental semiconductors, germanium and silicon. It records 1.2 volts approximately, but offers better electron mobility, making it ideal for high frequency and radio frequency application. Moving forward, much greater than that of gallium arsenide, we have silicon carbide, and its voltage drop is 2 to 3 volts, but its high breakdown voltage and thermal conductivity make it ideal for power electronics. So if gallium arsenide is for radio frequency and high frequency applications, you have silicon carbide ideal for power electronics. And we have also we have also gallium nitride because it is even higher voltage drop ranging from approximately 3 to 4 volts. It has ability to operate at very high frequencies and voltages, thus making it essential for 5G or fifth generation communication, radar, and high power electronics. As previously mentioned, gas or gallium arsenide has roughly around 1.2 voltage volts drop. So indium phosphide is close to that with approximately 1.3 volts drop, and it is used in opto electronics and fiber optic communication. To sum it all up, silicon and germanium energy that it loses or gains is expressed in electron volts.